Hi everyone, welcome to my channel and welcome to this video. So in this video I am going to discuss about a very interesting and useful Linux API which is called the Epoll. The Epoll set of system calls an API. So why is Epoll so interesting and what it does? Well, Epoll is what powers, or rather Epoll is the framework that powers event-driven IO in Linux, right? And if you think about it, presently is the dominant way how most of the web servers handle IO or tackle IO or serve a client request, right? Epoll is a set of APIs that power this entire event-driven or async IO on Linux, and to some extent also means that this is indirectly is what powering most of your web servers on the internet, or rather it is what powering the various internet services, because most of the internet services, as we know, is powered by Linux. They are hosted on Linux, and if we are talking about a service, it requires a web server, and that's where this API comes into picture. What we are going to do in this video is we are going to try to understand how Epoll works, why is it so efficient, and why it came as a replacement for the traditional pre-fork model where we would spawn separate processes to handle a separate request. Why that was not a great solution for the modern internet where things are at a very large scale. So what is it that Epoll does differently? And to understand it in a better way, we are going to build a very simple web server from scratch using Epoll, right? So it won't be implementing all the HTTP request methods, but we'll be implementing only HTTP GET, and we will try to serve files over the web server to our browser and to clients using the Epoll framework, and only the Epoll framework, right? No spawning of processes and stuff. And it will be able to handle concurrent requests just like a web server. So without further delay, as always, let's get started. Okay, so before jumping directly into implementation, let's first try to understand what was the problem with the older approaches that web servers had to to serve client requests, and what was the problem with that, and what exactly we are trying to solve with Epoll. Okay, so what a web server or any server that serves connection usually does is that, let's say we are talking about a web server, so its primary job is to serve some files or to act as a reverse proxy, right? So first job is that on its disk it has some files like f1.html, f2.html, etc., and there is a client and it sends it a request and it gets back a response. So let's say it sends a request something like get /h1.html http/1.1. So basically what it means is that client is basically making a HTTP 1.1 request for a resource called h1.html, and it expects some response. What the web server would typically do is it would get the request, parse it, see that, oh, the client is asking for h1.html, it would read it from its disk, and it will send it back in form of a response with the proper response headers: 1.1, 200, 1.1, let's say 200, okay, and you get the contents of the file, right? Simple. And then the file can be displayed on a browser, or it can be sent to a client, whatever, depending on who called it. If we go inside the web server, like what typically is happening is pretty much it's a socket program, right? It's typically a socket program. We create the socket thing. Let's say it uses TCP, so it creates a TCP socket, it binds it, and then it goes to a infinite loop sort of thing. And what it would typically do is it would first accept a connection, right? Once it gets a FD from the connection, then it will read from that FD, and it will process the request, read from disk, read the file from disk, open the file, read the file from disk, and it will write it back to the FD, right? And that's pretty much it. It will write it back along with all the HTTP response message and the headers and and everything like that. So in this case, the what it reads is pretty much this request data. Sorry, this request data is pretty much what it reads, and it parses it and it sends it back. So the problem with this approach, it's a single threaded approach. So the web server is pretty much serving a single connection at any given point of time. So probably we will be setting before creating once the socket is created, we will be calling the listen call to set up the listen queue. But anyways, even then, what would happen is that while one request is being served, that is the file is being read and written to the connection, if during the same time there is a new request, it will go into the queue and it will be waiting, right? So it's not a very good experience. It's a pretty bad experience for the client, because it's synchronous, like only one request gets served at a given point of time. So now, in order to fix this, what was initially done is, with the power of multiprocessing and multi-threading, the natural solution that comes to this problem is, you take help of multiple processes, right? So what we now do is that, once again, we create the socket, we create the TCP socket, we listen, we set the socket to listening mode, and we set up a queue, the queue length, we then bind it, and now in our loop, what we do is we first accept a connection, like it's just pseudocode. We accept a connection using the accept call, and then once we have a connection, what we do is we fork a process, right? We fork a new process, and inside child process we simply spawn a worker. Basically, this child process is the worker process, and in the process we simply call the worker function, and we pass it the connection FD. And in parent, what we do is we simply add worker to list of worker, and we wait, because it's a process, it's a child process, right? You need to wait for it, you need to manage it, you need to repeat and all those kind of things, right? So now the heavy lifting of actually processing the request, reading the file, serving it back, and then ultimately closing the connection FD goes to the child. So now the child will kind of parse, so the worker will now parse the request. It will open the required file to be served, it will read it, open file, read file, and finally it will write it back to the connection FD, right? And once it has been written, it will, of course, it will naturally close it. Close it. Okay, cool. And this worked perfectly fine, right? It's no more synchronous. By synchronous, I mean it's no more one by one, like it's not processing one request at a time. Whenever a new request lands up to the server, it's spawning a process, and that process is doing all the heavy lifting of creating the of reading the file, processing the request, and all those kind of things, right? But again, there is an inherent problem with this method as well. Initially it worked fine, and even some of the web servers still present today uses this kind of model. For example, the early HTTPD web server, also later rebranded as Apache web server, use something called the free fork model, and this is pretty much this method, right? So what Apache would do is that initially when you are initializing the server or starting the server, it would create a pool of processes, right? It will create a pool of processes which would stay standby, right? Whenever there would be a new connection, it would be handed over to one of these processes, and once this pool of processes is exhausted, which means there are, let's say the pool of processes had got 5 standby processes, and all 5 processes are now, they are serving something and they are busy. What the Apache would do is it will fork a new process, and it will let the incoming request be served by that process. And then there would be several configurations, like what is the maximum number of cold processes, that is standby processes, that can be there, what is the maximum number of newly forked processes that Apache can fork, and all those kind of things. But again, the problem with this approach is scalability, right? You cannot scale to something like hundreds of thousands of requests with this model, because you will soon be exhausting your server's memory by creating more and more processes. So later, going down the road, what happened is that we came up with something which is a lightweight version of process, also known as threads, and we replaced a process pool with a thread pool. But even with thread pool, although we shared memory, even then, like, there are kernel data structures which are required to be created for representing a process and a thread in kernel land, right? So no matter what you do, you are wasting, you are using of memory. And the other problem with this method is that this memory that you are allocating is often going to waste, right? It's not being, these processes and these threads that you are spinning up is it's not something which are being used continuously, like they are not performing something continuously. Why? Because web servers are inherently IO heavy processes, right? Web servers inherently do IO heavy tasks. So what I mean is that in this worker process, most of the time it would be doing IO, right? So first it will read the data from the given connection, right? It will read confd, and then it will parse it, it will open it, read the file from the disk, and again write back to confd and close it. So if you see, parsing is one of the place where it might be doing some CPU work, and if things like SSL offloading and those kind of things are happening, then that would require compute. But otherwise, most of the time what the process is doing is it's IO. It pretty much waiting on IO, like reading from the connection is IO, opening file and reading file from the disk is again IO, and writing back to connection FD is again IO, right? And the process is not necessarily doing any effective work during that time. It's simply waiting on IO. And the other reason why it's waiting, and this waiting time is not a ignorable time, is the server network might be a very fast network, but the thing is that consumer networks or client networks is not guaranteed to be fast. Rather, it's assumed to be slow. So your web server network is fast, but your client network is slow, which means you are spending more time on reading and writing to your connection sockets or connection FDs because of the slowness of client-side network. So how Linux would usually solve it in a multi-process environment is when a process is spawned, when one process is handling a request and it goes to sleep because of IO, it would schedule another process during the same time. But the problem again is the same, that when there are too many connections and there are too many processes, you are exhausting your system, you are putting pressure on your system's memory, and not only that, those processes are ideally not doing much during their life cycle. Most of the time they are waiting for IO. And overall, this entire framework or this entire system of, or this entire approach is not scalable, because you can only spawn so many processes, right? You cannot infinitely keep on spinning processes. So that's the issue with this approach of pre-fork or creating processes for every request. So now that we know what are the problem with the process pool or the thread pool model and why it can't scale, let's look at the event-driven approach or the Epoll API and how it helps. So before going to how it helps to solve this problem, let's first understand what is Epoll and what it actually does or how it works, right? So let's have a look. So Epoll, the API on which we'll be focusing today, it's basically a successor to other event-driven or event-based APIs in Linux. The first one created was select, and this is present on Unix as well. And then from there, from after select, there came poll or people, and after that, as a successor to poll, there came Epoll. We'll be starting with Epoll since I want to focus most of the time on Epoll. I'll be briefly touching on select and poll. I mean, it's just a heads up on what select and poll used to do, but I'll be mostly focusing on Epoll. So with event-driven IO, why we call it event-driven is we do not want to again and again wait for something, right? So we do not want to waste time by blocking on a read call on a socket file descriptor on a connection FD, right? What essentially we want and why we call it event driven is we want the kernel to notify us, like the user program, when some event occurs on a file descriptor, when there is data ready to be read from the file descriptor, or when it's ready to be written some data to the file descriptor. So bottom line is we want the kernel to notify us whenever there is some event occurs on a file descriptor of our interest, right? We have a set of file descriptors. We want the kernel to watch them, monitor them, and we expect the kernel to let us know when something interesting has happened with the file descriptor. So that's the bottom line of Epoll or event-driven IO design in general, right? We do not want to do the waiting part or the checking part. We want the monitoring part to be taken care of by the kernel. So let's see how Epoll does that. And soon then we will see how we can apply this thing to our web server problem. So again, Epoll in itself is not a system call or a library call. It's a set of calls and a file descriptor. Epoll essentially creates a file descriptor which we use to operate on Epoll, and it provides us with a set of APIs, syscall APIs, to use that Epoll and the member file descriptors that we want to monitor. So essentially, as an overview of Epoll, what Epoll expects you to do is it expects you to register. Like the first step is it expects you to register a set of interested FDs with Epoll, with an instance of Epoll. I'll soon say what I mean by an instance of Epoll, but it first expects us to register a set of interested FDs with Epoll. So these are the FDs which we are interested to monitor, right? It can be a socket FD, it can be a pipe FD, it cannot be a normal file FD due to complications added to a regular file FD. But the things that we are allowed to register with an Epoll are things like pipes and socket FDs. And we also, while registering, we are also expected to provide the events for which we want to monitor these FDs. So these can be things like poll in, which means when data arrives at the file descriptor, poll out, which means when is the file descriptor ready for writing something to it, and various other things like Epoll hop, Epoll error, and things like that. Out of these, the most, so again, these are not just poll in and poll out, it's Epoll in and Epoll out, and these are macros, so it will be in caps, but I just wrote it in small just here. But soon when we'll be implementing, we'll see that these are basically macros and we'll have to write in caps. But anyways, so most important, perhaps, I mean all are important, but the things that we'll be interested in most are Epoll in and Epoll out. Epoll in means that the FD is ready for read operation, and Epoll out means it's ready for write operation, right? And Epoll hop is when the FD is closed by the other end, so you know it's time to remove that FD from the set of interest FDs. So again, which brings me to the fact that you can add interest FD to an Epoll instance, and as well as you can remove it from the set of interested FDs of an Epoll instance when you are no more interested in finding out whether events are occurring with that on that FDs. And all these register, deregister, these are performed using a system call called Epoll CTL. Epoll CTL is the system call you will be using to add a FD, remove a FD, and all those kind of things, right? Basically all operations on a Epoll instance. Finally, there is something called wait, or basically the concept of waiting for an event. So what you do in this case is you pretty much call the Epoll wait API, right? Or the Epoll wait system call. What it does is that it waits for the kernel to notify it, or notify the Epoll wait for some event that has occurred on one of the, or a set of the, or subset of the FDs of the interested FDs. So it will pretty much monitor all the FDs present in the interest set, and whenever an event occurs on any one of the, or any subset of those interested or interest FD set, it will let this Epoll wait, it will notify this Epoll wait that an event has occurred, and it will also send back the list of events that have occurred, and those list of events will also have the corresponding FDs on which the event has occurred, and then this will be sent back to the user space program, and you can act on those events whatever you want to do, right? So it's like a continuous loop. And before I move further, the entry point to this entire framework is pretty much Epoll create, and what it does is that it creates an instance of Epoll, and it sends back that instance to your program, the user level program, and that instance is nothing but a FD. Commonly it's denoted by EPFD. right? So EPFD is usually the name used to denote this Epoll FD. So whatever call you are making, like Epoll, CTL, Epoll, wait, all these calls will take EPFD as a parameter to know which is the EPFD, which is the Epoll FD on which it's supposed to act. So this is the overview of Epoll. You first create a Epoll instance using Epoll create, then you register a set of interested FDs, like our interest FDs. Then you register a set of FDs which you want to monitor using the Epoll CTL system call, and while registering you also tell Epoll what are the events that you are interested to monitor. And again, and by the way, you can call Epoll CTL as many times as you want, because you might want to register newer FDs with the Epoll instance, and this is specifically what we are going to do while designing our web server, because as and when connection FDs would become available, we would add them to Epoll to monitor. Then finally there is Epoll wait, which simply returns when there is one or multiple events that has occurred on a subset of the FDs which we are interested in monitoring. So that's Epoll, and this is how it works. And the final thing that we would want to know about Epoll from the point of view of event-driven IO or our web server is, like, what are the two modes in which Epoll operate. It operates in the edge-triggered mode and the level-triggered mode, and let's see what these two things mean. The two modes in which Epoll works is, the first one is edge trigger. I'll be discussing it first. It would help me to discuss level triggered better if you already know what is edge triggered. This is not the default mode. The default mode is level triggered, but we'll first start with edge triggered. So if you want to use this, you have to pass something called Epoll et macro when you are adding a file descriptor to the list of interested file descriptors. So what Epoll et or Epoll edge triggered usually does is that it makes Epoll monitor the file descriptor in edge triggered mode. So what it essentially means is that, let's say you have registered 3 FDs, FD1, FD2 and FD3 in the interested in the list of interested FD list. Now let's say all these file descriptors are ready to be written to or ready to be read from. Let's take the read example. So let's say all these FDs are now ready to be read from, right? However, although they are, you can perform read operations on FD1, FD2, FD3, but actual data has arrived only on this FD. So let's say FD1, FD2 and FD3 are basically socket FDs. These are socket file descriptors, and let's say although 3 of them are ready to be read from, but actual data has occurred actually on FD1. So if you're monitoring all these 3 FDs in the edge triggered mode, and let's say data arrives at FD1 as we were just discussing, Epoll wait will get triggered, but it will have event only for this file descriptor and not for FD2 and FD3. Or rather, let's say if data has not occurred on any of these file descriptors or socket FDs, Epoll wait would never get triggered, or it would never return. It will keep on waiting. So what edge triggered essentially does is that it gets fired, or it notifies Epoll wait only when actual data has occurred on or has appeared on one of these FDs or a subset of the interested FDs, right? In the hindsight, what this actually means is that, let's say data appears on FD1 and Epoll wait gets triggered. It returns us event for this FD1, and you read, let's say from FD1 some let's say you read 10 bytes from FD1, but in reality FD1 had got 20 bytes, right? And then again you go to you process this 10 bytes, and then again you go back to Epoll wait. Now if you expect that Epoll wait will again get triggered because FD1 still has got some remaining data and it's always ready for read operations, you are wrong, because Epoll wait will not get triggered because the files are being monitored in edge triggered mode, which means it will get triggered only when the next set of data appears on FD1 or on any of the FDs. Just because some of the data is still remaining on FD1, it doesn't mean it will get triggered, right? So that's why we call it edge trigger. So it gets triggered only when something happens, not when something is ready. Okay, But you might not want this case all the time, right? You might not want the epoll to work in this mode all the time. Like you might sometimes want to get notified whenever a file descriptor is added and it's ready for read operations. You might not always want to wait for when the new set of data has arrived on the file descriptor. So it gets triggered only when data arrives, right? The counter mode of edge triggered is level triggered, which gets triggered whenever FD is ready for the desired operation, right? So now if you have FD1, FD2 and FD3 and they are ready to be read, right? Doesn't matter if new data has arrived or not arrived. As long as you have FDs registered with the epoll instance in the interest set, and whenever they are ready to be read from, epoll wait will get triggered, right? And it will return all the three. If all the three FDs are ready to be read from, they will return all the three FDs and you can read from them or do whatever you want, right? It doesn't wait when new set of data arrives, or it doesn't wait for that edge when new data arrives. Or you can draw an analogy with signals here, like electronic signals here. It doesn't wait for the time when the signal changes its states, but it pretty much gets fired whenever the signal is there, right? In any state, it doesn't wait for the state change. So that's the two mode that's there, and we will be using both these modes while designing our web server. So let's see how we can do that. Okay, so now that we have the knowledge of how epoll works and how the epoll set of system calls work and what they do, now let's see how we can apply this knowledge to our web server design, right? What we are trying to achieve is use epoll as an alternative event-driven system instead of spawning multiple processes to process incoming requests, right? So that's what our main target is. So let's start with what a server socket would usually do to serve client requests. So first, as usual, we will create a socket FD, and that comes from calling the socket API in Linux, and then we will put this socket on listen mode. So we'll pass the sock FD here, and then we will bind it, of course, to some IP and port, right? So now pretty much our server is bound to a IP and port, and it will start listening, right? So now what we would have done in a classical case is that we would immediately go into a loop and start and call the accept system call, and which would block us, and we would block on the accept system call to wait for incoming connections. But we won't want that. We want the kernel to notify us when there is a connection waiting to be served on this listen FD, right? Or this server FD. So for that, what we will do is we will ask. So I'll be using epoll. I'll be using just pseudocode here. Register sock FD with epoll, right? And now what we will do is, once we have registered it with epoll, we will wait. We will actually we will first start our event loop, right? We will start our event loop, and then we will say wait on the EPFD. Basically, we will call the epoll wait call to wait on the epoll instance that we just created and to which we registered the socket FD. Right now, what we want to keep in mind is, right now at this point we only have one, on the first iteration of the loop rather, we have only one FD registered with this epoll, and that is the server socket FD, right? Okay. So when I'm waiting on the EPFD and when the wait call returns, I will get a FD, of course. Like from the event I'll get a FD, and there are two possibilities. And again, the one thing that I've missed is, when registering this socket FD, I would definitely want it to be monitored for epoll in, because I want to monitor when new connections are coming on this socket FD so that I can get that new connection, right? We will use other flags as well, but epoll in for sure, right? So now I am waiting on epoll FD, and when I get a FD from this wait system call, there are two possibilities. This wait FD, the FD that's returned from the wait call, can be the socket FD. I mean, this socket FD that I just registered, or it can be a connection FD. How it can be a connection FD, we'll find out soon. So this FD, what we will do a if. So on this FD we will do a if. So if it's a socket FD, so if it's a socket FD, what we will do is we'll do our usual stuff. So if the Epoll returns us this socket FD, it pretty much means that there is a new connection waiting for us to be accepted on this socket FD. So we will simply do con FD equal to accept and pass this socket FD, basically our server socket FD. Right, now we have a connection FD on which new data might come, right? The client would want to send some data, send some request, right? The HTTP request. So rather than doing a read call immediately on the con FD and then do the write and in that classic way, what we would do here is now instead we will also register this, we will register this con FD with Epoll, right? And once again we will also register it for the event Epoll in, because we want to know when the new data is coming. But bottom line is we will also register this con FD with this Epoll, the Epoll instance that we have created. So now what we are pretty much telling the kernel is that along with a socket FD, this new connection FD that I received from this socket FD, you need to monitor this connection FD as well. And whenever there is data, this newly arrived data on this connection FD, let me know, I'll process it, right? So that's why when I said the wait system, the Epoll wait on this EPFD can return a socket FD and as well as connection FD. This is the reason why it can return us a connection FD as well. So that's why we'll always check which kind of FD we are getting. If it's a socket FD, we will do a accept call, we will get the connection FD and we will put it to our list of interested FDs, right? Now what if this wait call returns us a connect FD, which means some data, so the client has requested some, sent some request data on this connection FD. So let's go to the else part now. If it's a connection FD, it's pretty easy. What we will do is we will simply data equal to, we will read from this connection FD, we will parse the data, and then we will do the usual stuff, like we will open the particular resource on the server disk, we will read from it, and finally we will write. We will write it back to the connection FD, right? As simple as that. And now at this point you could also close the connection FD because it's pretty much done, right? And or you could keep it, or you could pretty much keep it open, and along with Epoll in, while we are registering the connection FD, you could also listen for something like a hub, like a Epoll hub event, which simply means that the client has closed the socket, and when that event occurs, you can simply close the FD, the connection FD, and you can remove it using Epoll del from the list of interested file descriptors as well. But anyways, that thing we will get to when we are actually implementing it, how we can optimize those things. So that's our usual flow that would happen with the Epoll when we are using the Epoll framework. So first we will create the socket, we will bind the socket to an IP port, we will register the socket FD with the EPFD, the Epoll instance, and we will start waiting on that Epoll. And whenever the wait returns, it can be either of the two things. It can be a socket FD that had an event, or a connection FD that had an event. If it's a socket FD, the event would mean that there is a new connection on the socket FD, and what we would try to do is we would try to accept the new connection, and we would register that connection FD with the Epoll instance, right? And if it's not the socket FD, if it means it's a connection FD, and then we would try to process or serve the request, whatever data it is there on that connection FD. Then we can either close it or wait for the Epoll hub event and then close it, or whatever. So now we have completely converted it from our usual read write syscalls to a event driven design, where we are basically asking the kernel to notify whenever there is a new connection or whenever there is a new data on one of the existing connection FDs. By the way, you can keep on accepting connections and putting it into the Epoll instance and ask the kernel to notify us via Epoll when new data is arrived. Okay, so now what's the problem with this approach, right? I mean, okay, so our code is not blocking on any portion except the epoll wait part, where it's blocking for an event to occur, which makes sense because if there is no event, what would our server do anyways? So the problem we will face here is pretty much analogical to what we would, or pretty much similar to what we would have faced in the first version of the imaginary web server that we were designing, where there would be a single loop. Inside the loop there will be an accept, then there will be a read, and then there will be write, and that way. So imagine like we get a confd event gets activated. There is some request data on one of the confds registered for which we are monitoring, and that client has asked for some file or some resource on the server. We open the file, and let's say the file is somewhere around 10 MB, right, in size, and we start writing it to the connection FD as an HTTP response on the connection FD. So it will take some time, right? Like if it's a 10 MB data, it will take some time. And at the same time, let's say we have another event on a separate connection FD, that a separate client wants to ask for some file, maybe not the same file but a different file, which is maybe way smaller than this 10 MB file, maybe some in kilobytes, right? It's a very tiny resource. Now, since this request, the big file request, came before the small file request, that the other request will be starved, right? It has to wait for this event to be completed, right? So that's again a problem that we have now put ourselves into, which is again the problem of degrading UX, where the clients would have to wait for some other request to be served completely first before the new one can be served. So this is a classic case of starving, where a bigger entity or a bigger request is starving a different client with a smaller request, right? How we can solve it? So here we can pretty much, what we can do is, instead of trying to fully serve the entire 10 MB file in one go to the connection FD, what we can do is we can chunk it up, right? What we can essentially do is, in this part of the code, right? In this part of the code, in write, we never try to completely send. So again, this write is just an example here. In reality, it won't be a single write. We would perhaps want to loop over the file FD, the server resource file FD, read it in buffers, read it in certain sections or in chunks, and then send it to the confd. But the problem is we are doing it in one go, and we should not be doing that. What we should ideally do is we read, let's say, 128 byte or 512 bytes from the file, send it to the confd, and loop back to the epoll wait call, right? And what happens that way is we are not starving any process, because we are not starving any request, because we are not trying to send the entire data in one go. So what I'm trying to say is that on the first attempt, just read 512 bytes of the 10 MB file and send it to confd, and again go to the next file or next event in the loop and process that again, whatever it has requested for. If whatever it has requested is within the 10 kilobyte boundary, 10 kilobyte limit, then send it entirely, or else again send just 10 KB, then go to the next event, then serve that in parts. Then like this, you time share your resources across all the events in an equal manner, such that no one gets too much of the resources and such that no one gets starved, right? So let's say epoll wait returns you 10 events and 10 corresponding FDs. So for each of the FD, you find out the resource that it's wanting, you open the resource, you read 512 bytes or whatever chunk size, you send that, you go to the next events for FD, again you do the same thing, you open its demanded resource, send 10 kilobytes, and like that you keep looping over all the events until it's done, and then you again go and wait for the EPFD wait to return, right? It would be clearer when we implement it. Again, the inherent problem here in this case, if we want to chunk it, right, what we are trying to do is that chunk the resource and send it to confds. That's what we are trying to do here, right? Now remember, in this case, if we go with the edge triggered, this won't help us, because edge triggered gets activated whenever an event has occurred, like whenever a FD becomes write ready or read ready, only then it goes off. But in this case, epollate or edge triggered won't help us, because no new event has happened on the file, right? No new event has happened on the connection FD, but still we want to write to it because we are writing by chunks. Until and unless the entire file has been written to the confd, we do not want to stop writing. We are time sharing among the different confds, but At the same time, we want to make sure we have written the entire data to confd, right? So we cannot trust Epoll edge triggered mode for connection FDs, but we will have to switch to level triggered because we want to continuously write to it unless and until we have written the entire resource to the connection FD. Again, it might sound a bit confusing, but I hope it will become clear once I start implementing it. So the bottom line is we are going to use Epoll set of calls to wait for the events for both for new connection and new request data. And once we have the new connection, we start monitor those connections as well. And if we have new request data on any of the connection FD, we read the request, parse it, and send back the data in chunks in a time shared manner across all the requesting FDs, right? And see the beauty of the process. Here we are multiplexing. The correct term here would be multiplexing. We are multiplexing IO over multiple clients over here, but we are not spawning different processes. We are concurrently sending data to each and every requesting clients in the same loop, right? In the same loop, but we are not allocating a separate process, and in that process separate kernel data structures and all the baggage of a process for a given request or a given client, right? So that's the reason how Epoll can do the same thing that a multiprocess thing can do with a much lower overhead, right? So that's the concept of Epoll and how we can use it while designing a web server. And several modern web servers use this logic or this way to serve requests. Nginx being one of the most famous and eminent examples out of those. So Nginx follows something similar, and we can this concept of chunking we not only can employ while writing something to the connection FD, but also while reading from the connection FD. Imagine a client wants to upload a 100 MB file to a server using a post HTTP call. What do? You cannot keep on reading from your client network, right? As I mentioned, client network is always slow, is always assumed to be slow compared to the server network. So what you do, once again you chunk it, you read in parts from the request, and you keep putting it in a buffer, and you keep putting it in the file where you want to store it. Let's say it's a multi-part form. You are pretty much like you are uploading a file. So you read the file or read the data in chunks from the connection FD, and you put it in your buffer or on the disk. So ideally you can use this concept of chunking in both the cases, and that read can also happen in a time shared way. So let's say there are 10 clients trying to upload 10 files to your server. You can read those files in a time shared way by multiplexing the IO, right? You read a 10 KB from connection 1, 10 KB from connection 2, 10 KB from connection 3, and you keep doing it unless the entire file from all the connections has been uploaded to your server, right? So that's IO multiplexing using Epoll. Right, so now that we know what is IO multiplexing, how Epoll works, how we can apply it to our web server design, let's build a web server from scratch where we will be able to inculcate all these concepts, and it should be able to serve resources to clients without blocking any clients or without having the need to spawn multiple processes. So let's do it. I have already created a easypoll.c. So easypoll is what we are going to call our web server, and it's right now blank, and I've already created a makefile, and it's just a simple makefile with build, clean, and run as usual. So let's start with the implementation of our web server. So we'll start with the usual stuff, that is including our header files. So now we are done with all our includes, and now we'll define some constants in form of macros. So there is a port on which our server will be running. So maxcon is basically the size of the listen queue. This is the size of the default response, like if client wants a file that doesn't actually exist, so we'll send a 404. So all those kind of default responses, we will be using this as the size of those buffers. I'll be I'll be speaking about all the constants when as and when I'll be using them. Okay, so now let's start with the main function, not the main the C main function, but the actual function that will run our server and run our event loop as well. And then the main function will simply call this function. So I'll call it run server, and I'll define some variables. Sock opt is just to set some socket options. Mostly I'll be setting the socket and the socket FDs and the connection FDs as non-blocking. We'll be using the buff array for various read and write operations. And quickly I will declare a string for our responses, our default responses. So remember, all the servers have a server root, right? Usually it's something like www where all the resources are present which can be served to clients. So we will create a server root here, and we'll call it www, which means we also need to create a folder of the same name, which will be empty right now. Actually, let's go ahead and create a tiny index.html here. We could have done it later as well, but let's do it right now so that we don't forget later. It's just a simple HTML file. So that's it. Now we will create our events array, right? This array will be populated by Epoll when it sends us back the events that have occurred on the monitored FDs. And finally to socket ADDR in types for our server and client addresses. Struct socket, no, it should be socket ADDR, my bad, sorry. Okay, so now I'll create the let's first get the server socket creation and all those usual server socket setup out of our way, and then we can discuss how we will do that. Let's first create the the basic Epoll setup, and then we will go into how we can chunk the data and timeshare our resources across multiple file events and all those kind of things. So we'll come to those later, but let's first get done with the basics. Just the normal socket call, and I will just set the SODU's ADDR socket option, right, so that we can reclaim the interface or the IP address to rerun our socket when we kill it using Control C. So this is really handy when you are testing stuff and you multiple times kill your server with Control C, and then you again want to respawn it. Okay, so we have our socket and we have made it. We have set the socket option so to use ADDR. Now let's set up our socket and attach an address to a socket. Let's create a, to keep things clean, let's create a tiny function for that. I'll call it setup server socket. And there is a typo. It's a good practice to set all 0, initialize it to all 0. So I've set the source address to INADDRNE, which means it will listen on all interfaces, right? And finally, I assign the port, which is the server for port macro 55555, and that's pretty much our setup server socket function. Quickly call it. We'll quickly call it here. Setup server socket ADDR, and then of course we'll bind the socket to that address. Okay, so my bad, this is not for attaching the address to the socket, but to set up our server address. The attachment happens of course in the bind, as a part of the bind system call, which we are doing right now. Struct, pretty usual stuff. Struct sock ADDR, not ADDR in, but just ADDR, and that part always confuses me, but yeah, it is what it is. Now the socket is bound to the address. Then what we are going to do is we are going to listen on this server socket, and the queue length will be maxcon. Then once our server is in listening mode, what we are going to do is we are going to define an instance of Epoll for our use case. So the Epoll FD, we will call it EPFD, and then we will use the first Epoll system call, that is Epoll create, and this basically has to be any non-negative number. It's no more used right now, the parameter of Epoll, but it still requires it for backward compatibility, I believe. So it can be any non-negative number. And then what I'm going to do, I'm going to add the listening socket or the socket FD or the server sock FD to this Epoll instance, right? For that, I'm going to create a tiny utility function. Let's quickly do that. I just don't want to clutter the main run server function, so I'm just going to create this tiny utility functions to do things like this, and I'll call it void add FD for events, and the first parameter will be the Epoll instance FD, then the FD that I want to add for monitoring, and the events. So this will be basically a bitwise OR of all the various event type macros. We'll see in a moment. Then I'll create a instance of a variable of types Epoll event, and this is a variable, this is the struct we would use to store the FD and the events for that FD, and we are going to use this struct to add the FD to the Epoll instance. So let's do that. ev.events to events, ev.events data dot fd equal to fd, right? And let's see why it's giving this thing. Struct epoll env, my bad, it will be event. Okay, and then we will use the second epoll syscall, that is epollctl, and we will do a epoll fd add fd and ev. And we will do a p error. If epollctl fails, so we will exit. Ideally, if epoll addition fails, we should not exit. The reason being, like, we should ideally differentiate between the server socket FD and the con FDs. If server socket FD addition fails, it means pretty much the server cannot start. So it's safe to fail the. It's better to early fail the server program. But let's say addition of a single connection FD to epoll fails, you would not want to fail the entire server program because your other connection FDs are there, right? So they might be, so your server might be already communicating with those clients. But in this case, since it's just a toy server, I'm going to simply early fail the entire server if ever epollctl fails. Okay, so that's done. And now what I'm going to do is use this function to add the server socket, and I'll provide a bitwise OR of all the events that I want to listen for this FD. So definitely epoll in, epoll out. Actually, to be honest, I don't need epoll out on this FD, this server FD, because it will only be incoming events. But anyways, I'll just put in epoll out for now. We'll see if ever we get a epoll out event on server socket FD. I believe we should not in this case, but anyways, I'll just leave it there. And then I'll get epoll let or epoll edge triggered. So as we discussed, like here we are not doing any sort of chunking or anything. We only want to get notified on the server socket FD only when some data has or some connection has arrived on that listening socket, right? We do not want the kernel to notify us all the time when it's ready to be read, but we want the kernel to notify us on the server FD or server socket FD only when a new connection, that is a new data, has arrived. So I'll put in the epoll edge as well, and now this is for storing the client address. I'll just create a tiny variable. And finally, we are at the moment, or we are at that position where we will now start with our event loop, right? Nothing but a infinite loop where we will be listening for events. And now we will use the third and final epoll syscall, that's epoll wait. Again, we'll pass epfd, which refers to our instance of epoll. And then we also need to pass it an array of type events, which it will populate with events that have occurred and along with their FDs. So let's first define that array actually. So it will be it's the same type as this one, which we use to register an event. And so let's define it here: epoll event events, and remember it's a list, it's an array. And the size we'll have is that of max events. Right now it's set to 32. We can, I mean, for web server it doesn't actually, for this web server it actually doesn't matter, but you can, when you're actually using it in some real world scenario, you might want to tweak the number of events that the kernel is able to return via epoll at a time using this number max events. Okay, so now that we have the events variable, we will simply send it here. It will take the length of the array and a final parameter which is a timeout. We do not want any timeout right now, so we will go with -1. -1 typically means it will block forever. Epoll wait will block forever, which is fine with us. And then we'll simply whenever Epoll returns, it means it has got some events and it has populated the events array with the events. So whenever Epoll wait returns, we will simply loop over all the events that we received, and then we will see what we can do with those events. So NFDs is pretty much the number of events it has received, and so we will simply loop over that. So if events I dot data dot fd, so the fd is put in data parameter or data member, and if that's equal to server sock, the same thing which we discussed, it means we have received a new connection. So let's accept the connection, and we will have to define a connection sock. Oh, we have already defined. So const sock equal to accept, the usual accept call. We will give the server sock, and we will do a struct sock addr pointer, and we'll do a client addr sock length, and we'll do a inet ntop. So we are basically trying to extract the address that the connection has to our client addr variable. This is pretty much usual socket stuff, socket address conversion stuff, nothing related to Epoll. So we are simply extracting the IP address and storing it in our buffer, and we'll do a client addr, and we'll simply log from where the connection is coming, basically the connection address or the client address, whatever you call it. Again, the IP is stored in buff, and for the port we'll do the usual conversion, which is N to HS, network byte order to host byte order for short, and we'll do a client addr dot syn port. And now we'll do one more thing. We will set these connection sockets, the connection socket FDs, to non-blocking mode. Why do we want to do that? Because we want to do it because we do not want to block on the connection sockets or the connection socket FDs while reading from them. Usually when we read from a file FD, what happens is when we have reached toward the end of the file and we try to read again, it returns 0 because the offset has reached to the end of the file and it doesn't block. But with FDs associated with sockets and pipes, it doesn't work that way. What happens is that once there is no data in the corresponding socket or corresponding pipe, what happens is the read operation will block and it will stay there. But we don't want that, right? We do not want to block. Once we have extracted all the data from the FD file descriptor or from the socket, what we want to do is we want the kernel to return a E again, right? E again means no data is present as of now, come back later, right? So we want to do that, and for that we need to set the socket into non-blocking mode. So once again, let's write a tiny utility function for that. Set non-blocking, and it will take one single parameter, that is the socket. Actually, we can simply call it FD. Quickly write this function. We will use fcntl sock FD FD comma f set fl fc till tf we will get the fc ntl properties of the file. We will bitwise OR it with O non-block to make it non-blocking, and if that returns -1, we will return. If that returns -1, we will simply return that. Actually, we could have simply returned the value of whatever fcntl returns, but anyways, never mind. Okay, so that's like setting it non-blocking. And now what we are going to do is we are going to call this function with consoc, and we are going to add this connection fd to our list of interested fds for monitoring. Once again, we will pass epfd, the newly received connection soc. Here we will monitor for epoll in, epoll r dh hop, epoll hop, and epoll out. And notice how we are not using the level triggered, the edge triggered option here. We want to go with the default level triggered thing. Why? Because we want to be notified whenever this file is existing, whenever this connection fd is alive. It's in a list of interested fds and it's ready for writing, because we are going to chunk the resource that's requested by client, and so that we can time share across all events, right? So we won't use edge triggered, but we will go with the default level triggered. So far so good. Now the actual fun starts. If event I dot events and epoll in. So if we receive a event of type epoll in on any of the registered fds, right, what we would assume is that it's a request data, or some client has sent some request data or http request message on one of the on that connection fd, and we will try to read the entire data, or the entire request data from the connection fd, and we'll try to process it, right? Again, for the reading part, we are not going to chunk it, right? We are not going to chunk the reading part, but we are going to chunk only the write part. So let's do that. We will read the data as long as we are not getting a e again, and since we are using quite a high buffer size, that is I believe 1024, buffer size is 1024 bytes. So in this case, at least all the time we'll be getting the entire HTTP request message into our buffer, so we don't have to chunk it, as I mentioned earlier. What I'll do is I'll say received, I'll simply log it, epoll in event on con fd %d. I'll simply mention which fd it is. I'll just initialize buff with all zeros. And now I'll start reading the FD. So what I'll do is read event I dot data dot FD. I'll read it into buff. I'll just send size of buff. If n is less than equal to 0, either we have received 0 bytes or we have received something which is less than 0, which is basically an error. Most likely in this case we will get a E again, which means all data has been received. We'll simply print likely to have received all data from request, and we will break this loop. And else, if it's not less than equal to 0, it means we have received the actual data. And again, I'm not going to loop over, I am not going to wait until n is less than equal to 0, because n is less than equal to 0 would be pretty much the case once after the very first iteration, because again we are considering that the request data is extremely tiny. It's just probably it will just be a name of a resource on the server, right? So very likely it will be within 1024, and we don't care about those data which is those request data which is above 1024. Likely it will never be the case in our toy web server. So just after the first iteration, we would likely to have the entire data received, and so the next iteration will be n less than equal to 0, and we will break the loop. So if n is not less than equal to 0, it means we have our request data. And what we'll try to do here is we will simply log again, saying that hey, we have received some data. And now the data is already in buff, right? Now the question is, what are we going to do with this data? This is a usual HTTP message, right? So it will follow the HTTP message format. We will have to extract our fields of interest from this data. So what are the things that we want to extract? Remember I said that this web server, this toy web server, will only be interested in the GET calls, no other HTTP methods. The other thing we need to extract is the resource name or the resource path where it's located. In this case, I'm assuming everything will be located inside www, so I'm only interested in the name of the file, and we are not going to support any URL paths like any sub paths. It will be only a one shot name, right? So we are going to extract that, and let's see how it looks, how the request looks. It looks like this, right? So this is the Mozilla web docs, and if we take a look here, we will see that it looks like this. It has the first, I mean, it's how a typical HTTP request message looks like is on the first line. Just before the headers, we have got the HTTP method, post get option head, like that. Then the request path, this represents root, and then the version of the HTTP call, right? So all we are interested is in the method and in the resource name. So we have to extract these two things, and the next part is nothing but typical string manipulation and string extraction. So let's quickly get that out of our way. So for that, I'm going to create a structure called request parsed, and in this request parsed struct, I'm going to store the different components of the request, only the interested components of the request message. So let's quickly define that. So that request parsed struct will have a type called request_t, and let's see how it's going to look like. So type dev struct here we'll have a method. I believe 20 bytes is enough, more than enough for storing the method. Resource, and we are going to limit it to 100 bytes, and so it will be fully contained within the buff size that we have defined, which is 1024. And let's do a request_t. So that will be the type of the request parsed struct, and I'm going to define one here. So let's define it here, and now we can use it to extract. We will again define a tiny utility function to do the string work. Let's quickly mem set this request parsed variable to all 0 so that we don't forget later. We'll also initialize the default response variable also to all zeros. In case it's a illegal request, we will send the default response. depending on certain criterias. And then we will create a function whose work will be to simply extract our fields of interest from the HTTP message into the struct request t. Let's see how we can do that. So let's create a parse request function. Of course, it will take a string, which is our request. It will take the address of our request parsed struct variable so that we can populate it. And I am going to use the handy strtok function to split our string and get the individual tokens. Not all, only for the first line and the first two tokens. So I'll call this first line strt okay request, and the delimiter will be \r\n, and we will also have, now we will start splitting the first line, and the first thing, remember, will be the method. So let's get that. Okay, we have got the method, and then the immediately next token will be the resource and strt. Once again we'll do strt okay. It's just how strt okay works. When you are splitting the same string or the same sentence, you need to pass null as the first parameter. And now, since we have got our required things, we will simply copy request parse dot method comma method and strcpy request parsed dot resource. That's it. Now we have got our parse request function ready, and let's use it to parse our actual request. Well, that wasn't that complicated because the scope of our web server is really tiny. But again, my main target is to show the power of Epoll, right? So no point in complicating the web server. So we are going to parse this buff into request parsed. Now we need to check what's the method type that's being used. So let's do strcmp request parsed dot method, and we will compare it with get because that's the only method we are interested in. If that's not equal to 0, which means the method that was used for this request is not get, what we will do is we will generate a typical 405 response, right? We'll return a method not supported or method not allowed response. So again, for that, once again I'll create a tiny utility function whose only work is to generate this response 405 response and populate the default response RESP variable with this, right? That's why we memset RESP, because that's what we'll be using for this purpose. So let's do that. So void generate 405 response char star buff. I will now generate the response string response. Spelling is fine. So it will be 1.1. Typical 405 response. 405 method not allowed \r \n. So remember, the delimiter for the various lines in a HTTP request and as well as HTTP response message is \r\n and not just \n or just \r. We need to use both, or else our HTTP client, for example curl, or the browser won't be able to parse it. So this is a very common source of bug, and which you might spend some time trying to debug. We'll just have a server header. We'll call it Epoll, the name of the server, and another content length header. In this case, our length of the content, basically our response won't have a body, right? So the content length will be 0. Then \r/n/r/n, and then followed by a null body, because we don't have a body for this response. strcpy, and we'll copy it into the buff. We will dereference this buff parameter once because it's a double pointer. So one level dereference will give us the actual string which we want to populate, and we'll copy the response into that buffer. And you know what, I will create another utility function which will generate a 404 response, right? Because in case if the user wants a file which is not present on the www server root, we want to generate a 404 response. And it's pretty much the same thing. Char star response equal to http 1.1.404 not found \r/n server easy poll \r/n. Once again content length will be 0 \r/n \r/n. Yeah, that's pretty much it. And once again copy star buff response, done. Now if it's not equal to get, we will simply generate a 405 response and store it in RESP, and we will immediately write it back, right? No need to do chunk or anything because it's a tiny good old 405 response. .data.ft resp strlen. Yeah, so again we could have essentially closed the connection FD, consoc FD here itself and removed it from Epoll instance, but we have already registered this connection FDs with all the Epoll RD hub and Epoll hub, right? So we will simply just wait for the Epoll hub event, and on that event we will deregister or remove this connection FD from Epoll instance. That's just a more systematic way of doing it. So now we will try to open the resource that's requested in the request message, right? And for that, once again, we'll create a tiny utility function. We will call it open resource char star server root char star resource. So the full path of the resource would be pretty much /the resource. Ideally, we could have used absolute path for this, but since I'm going to run this web server mostly from this directory, I don't care, like I don't need to create an absolute path. So let's just make it as simple as possible. Path equal to char star malloc strlen server root plus strlen resource, and we will use sprintf, my favorite, to copy this entire to create the entire resource path. That's pretty much it. Why I did a %s and %s, not a slash in between, because resource will already be starting with a slash, right? Okay, so now I'll try to open it. path, and I will open it only in read only mode, because I don't want to write anything to it, right? So it makes sense to open it only in read only mode, and I will return this, whatever open returns, I don't care. But if it's less than, it can be many things, right? It can be file not found, file we don't have the permission to open the file, but I don't care about what the error type is. If it's anything less than 0, if it's any sort of an error, I'm simply going to report it as 404 file not found. So no 500, no nothing like that, just 404. Okay, so let's do open resource server root request parsed dot resource, because resource is the variable where we are storing the resource component of the request message. If RFD is less than 0, then we simply generate a 404 response using our utility function. And we'll straight away write it just like the 405 response. And if it's not less than 0, which means we were actually able to open the file and get hold of a file descriptor, then next thing which we want to do is to check the size of the file, right? Because we want the size of the file for our content length header, right? We have to know the size of the file that we are sending. So let's do that. Once again, you might have guessed, we will again create a tiny utility function to get the size of the file. File size int fd, and we will use the fstat call to get the size of the file. If fstat fd comma and st not equal to 0, it's just normal how fstat works. I mean, nothing special here. We'll say fail to get file size, and if we can't get file size, once again we'll send back a 404 response, right? Ideally we should have sent a 505, 500, like some server error, but I don't really bother doing that. I'll just send a 404, and it's a stat. No matter what, I'll send a -1, and I'll do a st.st. I'll return a st.st size. Now in the else part, I'll try to extract the size of the file equal to get file size rft. If f size is less than 0, generate 404 response, and once again write it to the FD straight away. Else now things will get interesting, because we are going to do the chunking thing, right? We are going to send the file in chunks to the connection FD. What we are going to do is, first we are going to generate the response header and the response first line, right? Because that will stay constant irrespective of the length of the file, right? So what I essentially mean is this part, HTTP 1.1 403 forbidden blah blah blah, the first half of the response, the entire response message except the actual data will always remain constant, right? Only thing variable here is I'm not going to send date and all these things. The only part that will change, it will be a simple content type text HTML. That's the only type of content I'm going to send for this server. Only part that will change is this part, the content length part. So I will immediately write this part to the connection FD, and the rest of the part I will chunk and loop, right? So once again, log the file size, that we are going to serve. And now what I'm going to do is I'm going to create a variable for sending the response prefix. I'm calling this entire part, this non-body part of the response, as response prefix. So I'll quickly create a variable for that, and I'll call it sp prefix equal to char star malloc default prefix. Actually, I could have repurposed RESP for this, but let's keep those things separate. And once again, I will create a tiny function to populate this response prefix. Create response prefix with content length. So I'll have a prefix buffer with default resp prefix size length, and then it's just once again as printf. It should be a double pointer, and what I'll do is http /1.1 200 OK /r/n content length %d again /r/n content type text -html /r/n /r/n. And now I'm going to copy this back to the provided buffer. That's it. Okay, now I'll do a mem set. I just want to clean the resp prefix variable on every run, on every time I use it, and I'll mem set it with 0, and then I'll create the prefix. All it takes is the buffer and the f size. For debugging purpose, I'll simply print the prefix that got created, and I'll straight away write this response prefix, right? I mean, no need to, as I mentioned, no need to chunk this part, and it's pretty much within our buffer size, so we can write it in one go. It's tiny, so we don't care. Prefix str prefix. Okay, so after we have written the response prefix to the client or connection socket FD, now what we have to do is start writing the actual content to the connection FD. So for that, since we are not writing the entire content at once, but we are writing it in parts, we need to keep track of the resource FD per connection FD or per client, right? So somehow since we'll be continuously iterating and over all the events and the corresponding file descriptors, and write the requested resource data to the FD, to the connection FD part by part until the full data is written. Till the time the full data is written and the connection gets closed, we have to keep track of the resource FD and the corresponding connection FD. So we need to maintain a mapping. So one very obvious way to do it would be to create a structure where the members will be the resource FD and the connection FD, the con FD, and create a linked list, basically a dynamic array of such structures, right? We could keep expanding an array, or we could use a linked list. However, we are not going to do that. We are going to create a static array where the index of the array would be the connection FD, and the data would be a structure whose one member will be the resource FD, right? So that's how we will create the mapping. Now the index will be the connection FD, and either we can directly store the resource FD as the index value. So I'll use a struct anyways, so that we can store more data if required, but it could have been stored as the index value as well. Now you might be thinking that how this thing would scale, right? And things like wouldn't it go out of bounds of the array, because we are going to store it in an array, and it might, like, the we don't know what would be the FD value be like, right? It can be any value, and the index of the array might not be sufficient for that, right? That's true, because I've used a linked list in this case, but I chose to go with a array. I mean, again, on the array it's as well we could call calloc and keep on increasing the array, but in this case I will be going with an array of a constant size, right? And that size will be 1024. I mean, we'll be using an array of the length 1024, and we'll be using the index of those array as the confd, and the value as the struct with the resource fd, right? Now, why this value 1024, and why would having a constant array length work in this case? Well, the value 1024, because this 1024 value is special. The reason being, remember the connection FDs that will get allocated for a client connection on calling the accept system call. This con FD will be allocated by the process, right? The process will be creating this file descriptor con FD, which will point to this socket, this connection, this socket connection. And this connection FD is nothing but a open file descriptor that will be created by this process. And on Linux, a process can only have a certain number of open file descriptors per session, right? So there is a limit on the number of open file descriptions per process per session in Linux, and this is controlled by ulimit, right? So there are two limits for this number, which we can look up using the ulimit command. There is a soft limit and there is a hard limit. So the default soft limit for users for this open file descriptor per user session per process is 1024, and that's the reason I have chosen this number 1024 to be the length of this array, which essentially means is that that no process can have more than 1024 open file descriptors per session on Linux, right? It cannot open more than 1024 file descriptors. Again, this is a soft limit. It can obviously be changed by the user. You can increase it you can simply go and edit the limits.conf file, but again, there is something called hard limit, above which you cannot change the hard limit. Just any random user cannot change the hard limit. They'll have to use a root to do that, and that can be, again, and there are various ulimits and various limits on number of open file descriptors at system level as well, which is set from proc/sys/proc/sys/fs file max. I won't delve deeper into this because ulimits is a whole thing in itself, and it might demand a separate video in itself, so I won't go into the details of ulimit. The bottom line is, that's the reason I'm choosing this value 1024. If I wanted to cater to more number of concurrent connections, basically larger number of simultaneously open file descriptors, I could have maybe increased the soft limit. There are a number of other ways that modern web servers employ to do this. For example, Nginx. What Nginx does is that it has worker processes. Again, it doesn't mean that it will create one worker process for every request. No, not that. What Nginx would essentially do is, depending on the number of cores that a system has, it will create that many number of processes. So if your system has got 8 cores, it would create 8 worker processes. Then every worker process would have this limit of 1024 or whatever open file descriptor limit, and then each such process could cater to that many concurrent or simultaneous open file descriptor or open connections. And let's say if each process could handle something like 1,000 open file descriptors, it means 8 processes could deal with 8,000 simultaneously open file descriptors, which means 8,000 open connections, and then that would overall increase the QPS of the server, right? So we can solve this problem in various ways. For now, I'm going to go with this. So there are a number of ways with which you can scale this: more process, dynamic arrays, or just increasing the soft limit or the hard limit on the number of open file descriptors. Various number of ways are there, but for this server, I'm going to go with a constant array whose size will be 1024, right? So first I will create another struct, which will be known as active client _t, and it will have only one member, which is FD. Again, you can directly store it at the array position, but I just chose to go with struct in case I want to store some more data in the future. And I will call it active client _t. Now what I'm going to do is I'm going to create an array of clients whose number will be a constant. Again, max con is already set to 1024, and I'll simply want to initialize this array with active client t structs. And I will just initialize it with -1. So now what I'll do is I'll initialize the active client at for this FD with RFD, right, with the resource descriptor that we just got. Once again, let's not forget the colon here, semicolon here. And now we are pretty much done with this branch of the if, where we were waiting for incoming events like read events. So what now I'm going to do is start with the write events, and it will be completely separate from the read event operation, because any of the connection FDs can be ready for being written to, and we will just check that if for that connection FD we have a active client entry with a non-negative resource FD, and if there is a non-negative resource FD, we will read certain bytes from that resource and write it back to the connection FD. Easy. So we will check that if it's a Epoll out event and events I dot data dot fd is not equal to server sock. We are not interested for Epoll out kind of events on the server sock. And if clients events I dot data dot fd dot rfd is greater than equal to 0, which means there is a valid resource against that connection fd. What we will do is we will copy certain bytes of data from the resource file and write it to the connection file. And for doing that, once again I'll go with a separate function. I'll call it copy from rfd sock fd, because I'm copying from the resource fd to the socket fd, connection fd. It will take two parameters. First one is rfd, second one is socket fd. I will assign a buffer, create a buffer of chunk size. We have already defined it as something like 512 bytes, which is fine enough. I feel our system shouldn't take much time to transfer 512 bytes. Could have actually increased it, but let's keep this so that I can show you what happens for a larger file. Dbuff chunk size, so I read this much, and it's greater than 0. I'll simply write to the socket fd that much data. If nread is less than chunk size. So when will be the number of bytes read from the file less than the chunk size? When we have reached the end of the file, right? Which means it's time to close the resource descriptor. Cool. And we simply return the number of bytes read, and we'll know in a moment why we want to return the number of bytes read. clients events I dot data dot fd dot rfd events. So we are simply going to copy the data from the resource fd to the connection fd or the con fd data dot fd. I keep saying con fd because that's usually the variable I denote the connection fds with. What I mean is basically the fd that I got from accept system call. Okay. So if inred is less than chunk size, which means we have already closed the file, what I'll simply do is clients events I dot data dot fd dot rfd. I'll set it to -1 so that I do not try to again send data to it, because the writing is complete. The entire data has been sent to the client, and probably now the client would probably close the connection, which would mean it will anyways be removed from the Epoll instance. We'll do it in a moment, and we'll do another login. Done sending data to fd. Events I dot data dot fd. Okay, so we are done with the chunking, the time sharing part of the thing of the web server. Now watching out for the socket closing, the client socket closing events, and removing it from the Epoll instance. Let's do that quickly. I dot events and Epoll rd hop and Epoll hop printf connection closed for let's just print the fd as well. I dot data dot fd Epoll ctl, and we will finally remove it from our EPFT instance. Epoll ctl tl del comma dot fd. Oh, why did I? No need for the braces. And what I'll do is I'll also close the. Actually, I'll first close it and then I'll remove it. Close events I dot data dot fd. Then I would remove it from the Epoll instance. Yeah, that makes sense. And pretty much that's it. We are pretty much done with our web server code. The last piece is the main function, and we won't be doing much here. We'll simply be calling the run server function, and that's it. That's our simple tiny web server in 224 lines of code, which utilizes Epoll to serve concurrent requests from various clients, different clients, and yeah, that's pretty much it. So now let's test it, compile it and test it. So for compilation, I'll simply use the makefile, and I'll try to do a make build, and let's see if it compiles. And it did not, so looks like there are some errors, and let's try to fix those. Okay, what do we see? Redeclaration of struct Epoll. Okay, 126. Okay, let's get rid of it. One more, and that's implicit declaration of function size of. Oh, that's a typo. On line 141, and it got compiled. Now what I'm going to do is I'm going to split my terminal, not vertically but horizontally. Yeah. Okay, so Here what I'll do is, here I'll issue the curl commands, like I'll use curl as a client, and then I'll see if we are able to access our web server. So we already have created one file, I believe, which contains this tiny HTML content. Okay, so now let's start the Epoll server, Epoll web server. I can simply do a make run, and let's now do a curl 127.0.0.1 index.html, and we got the response. So we got the request from curl. As you can see here, it's mentioned that user agent is curl. It sends so many things, but we are only interested in this part, which means we are extracting the method slash index.html, and that's it here. And this is the response we are generating. The response prefix, like file size is 48. The prefix is the first line is HTTP 1.1 200 OK. Content length is 48 and content type is text HTML. So first we accepted the connection from 127.0.0.1 47676. This is just a random assigned port for curl, using which it's making the request, and then we received the actual request event for the connection FD that we accepted from this from the server socket, and we generated the response data, and we finally sent it. And lastly, we closed the connection from that came from curl, right? So we accepted the connection, we read from the FD, and we wrote to the FD. We read from the file, the resource from the disk, and we wrote to the FD. And finally, once curl closed the connection, we closed the connection FD as well, and that's it, right? Okay, so that was pretty simple, right? Now what next I'm going to do is I'm going to now create a huge, not huge, but a pretty big file, and then I'm going to see if chunking is working, right? So what is likely to happen is that when one curl client is requesting the big file and it's getting the file and printing out the terminal, the other curl client, it will request for this tiny index.html that I just created, and that should work instantly, right? That request should not get hampered by the previous big file request, right? So let's try that. So here what I'll do is I will create another file, index2.html, and what I'll write here is pretty much simply, let's say this is a test. Let's just make it bold, just like that, for fun. Okay, so this is a test from Epoll, and now what I'm going to do is I'm just going to copy this, Control C, Control V, and I'm going to do it multiple times. Next I'm going to copy this entire line just to speed up the big file generation, and I'm going to pick again, do it multiple times. Okay, let's see how big is the file as of now. h dub. Oh, it's 329k, not that much. Let's take it to at least 1 MB. Is it 1 MB yet? Oh, pretty close. Let's just do a big chunk. Okay, now it's 2.7 MB. Pretty decent, right? That's decently big, right? And our chunk size is 512 bytes. So it would be doing quite a few loops to, or it would be creating quite a few chunks to send the entire data. And what I'm going to do is divide this terminal further and divide this one as well. Okay, so now we have got two files, index.html, which is this tiny HTML file, and index2.html, which is pretty big compared to index.html, right? And I'm going to start the server. Now what I'm going to do is, so let's just see that this one is working. Yeah, this one is working. And let's just also once check from the browser, right? let's just check from browser once as well that it's working, it's accessible from the browser as well. And let's do index.html, and it works, right? Now one thing we need to note here is that unlike curl, when we do a curl, you can see that it says connection is closed for this FD. Connection is closed for the curl connections FD, right? But when I do the same thing from the browser, you will see that it's the same old FD. It's the same old FD number 5. It didn't create a new FD. If I do curl again, it becomes 6, right? So why curl is always getting assigned the number 6? Because the FD is allocated to a process when it tries to open a file is sequential, right? It starts from 0, 0, 1, 2 are the pretty usual FDs. Those are the normal file channels like standard input, standard output, and standard error. And post that everything happens sequentially, 3, 4, 5, 6, da 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 da. And since the curl is just a single one-shot transaction, server receives the request, curl gets the data, curl closes the request, and the server would close the connection FD and remove it from the Epoll instance. So pretty much the file descriptor is gone. So next time when again we create the once again we do a curl request, once again it assigns the same FD, that is 6. But what we saw here is when we are making the request from the browser, Firefox in this case, we are again and again getting assigned the same FD. This is because you can see that the FD never gets closed, right? The file descriptor 5, FD5 is all the time open. But why is this? Why is there no SIGHUP event happening? This is because of something called keep alive. So if I open the network tab and send a connection, you will see that, let me just, if I zoom it, you will see that if I go to the headers and the request header, you will see it says connection is keep alive, which means the browser tells the server that the browser never sends the connection close event, or it never tries to close the connection from the client side. Since it's never closing the connection at its end, in this case we have designed this, or we have created the server in such a way that until and unless there is no SIGHUP event, it doesn't close the FD, so the FD is persisting. So ideally what a web server does, it checks for this header connection. If it's not keep alive, it would close the FD just after sending the data. But in this case we are not doing, and the browser is sending connection keep alive. The browser is not closing it from browser side, the connection remains open. Okay, so that's the reason we see that the connection FD for the browser is constantly open. And yeah, but that's fine. We need not be bothered by that for now in this case. Okay, so now what I'm going to do is I'm going to now call the big file and see if it's able to chunk it and give it to me. What was the name again? Yeah, it was index2.html, and okay, that was pretty fast. So that's not what we want. We want to, let's just increase the size of the file a bit more. I want the curl to at least wait for some time. So let's, by the way, let's just see if the big file is accessible over the browser. And it is accessible over browser, so that's okay. And that's expected, that's fine, it's working. Okay, so what I'm going to do is make this file a bit longer. I mean, I could have done the other way around as well. I could have reduced the chunk size, but never mind. Let's just increase the file size. Okay, so how long is it now? 11 MBs. Let's see. Let's just make it a bit more, bit bigger. Okay, let's see if we are able to simulate some long running connection, if we are able to simulate a long running file transfer or data transfer. in this case. So let's, okay, that's decent enough. So what I essentially want to make sure is that when curl is fetching this data, another instance of curl which is trying to fetch the smaller file, which is index.html, is able to do it pretty fast. Like it doesn't have to wait for this. So first I'll start this and see it. So that's, so first I'll start this, and at the same time I'll, okay, that was not a very nice demonstration. Let's start this. So while this is running, if I press here, it returns the right window, the call to index.html happened pretty fast, right? It just happened just like that, which means it was not being blocked by the first request. So it was not being starved. Both of the things happened concurrently, right? Because we time shared the events, right? So what happened is in the event loop across, we looped over all the events. We sent out 512 bytes to this curl instance 1. So let's call it curl 1 and curl 2. So we chunked out 512 bytes to curl 1, then we went to curl 2. For curl 2, the response was pretty much within 512 bytes. We sent it out all together. In the first iteration itself, it got its request back, and then again it continued with its 512 chunking of the curl 1 request, right? So, and the fun part is, even if another instance of curl tries to get index2.html, then also it should happen together, right? One should not get delayed for the other one, which is exactly what's happening here, right? If I do a, so that's FD5, that's FD6, and now FD6 ended, right? Okay, so can we get this huge file over, not huge, but yeah, 20 MB file over to the browser? Let's check that. And yeah, it's still getting it. Yeah, it got the entire file over browser as well. The browser was able to get the entire file as well. So as you could see that it took some time, like it was showing loading here on the browser tab, but it could get the file. So in ideal case, like 512 bytes is pretty less of a chunk size. I purposely capped it at 512 bytes to show this concurrency. But all our purposes are solved. We can do time sharing or resource sharing between multiple events or requests, which pretty much gives us the illusion of multiple processes, but it's not multiple processes. It's the same process doing an event loop, right? Concurrently serving multiple requests, or in other terms, we are doing IO multiplexing, right? That's how we can do event-driven IO using Epoll infrastructure in Linux. Right, again, Epoll is very specific to Linux. You cannot do it on Unix. If you are doing it on Unix, you would have to use select and poll or people, but Epoll is only for Linux. So yeah, that's pretty much it for this video. This is what I want to discuss. I want to discuss the very famous popular Epoll, which as I said powers a part of the majority of the internet servers, since they are all Linux and most of them run modern servers, and that's how modern servers take help of event-driven IO to scale without eating up too much memory for no reason. And yeah, do let me know in the comment section how, if you all have built your own web servers, and for what reason. Was it was it a toy server like this, or is it, are you serving live traffic for some real world purpose using that web server? That would be pretty interesting to know. And what approach did you take? Like, did you go with the pre-fork Apache pre-fork model, or did you go with a thread pool, process pool, or you did a event-driven design where you use something like select poll or epoll, right? So thanks a lot for watching this video, and hope you enjoyed it, and see you all next time.